There are many extreme phenomena in space, such as gamma-ray bursts, neutron star collisions, galaxy mergers, and, most famously, black holes. We often think of black holes as all-consuming dark wells, infamous for devouring even light itself. While this is generally true, it is not always the case, particularly for supermassive black holes, those millions to billions of times the Sun's mass, residing at the centers of most galaxies. Around these giants, the events are far from dark and often extraordinary. The supermassive black hole at the center of the Milky Way is relatively old and dormant today. However, observations of similar black holes elsewhere in the universe reveal a variety of dynamic behaviors. When active, these black holes are referred to as active galactic nuclei, AGN. Today, we'll explore one such fascinating type of AGN, the quasar. What is a quasar? A quasar is an ultraluminous and ultraenergetic type of active galactic nucleus. It occurs at the heart of a galaxy with a supermassive black hole millions to billions of times the mass of the Sun. In quasars, matter near the black hole moves at incredible speeds, heating up to such high temperatures that it emits extraordinary amounts of light and other forms of radiation. This radiation often outshines the host galaxy, allowing quasars to be observed from vast distances across the universe. To understand quasars, it's important to address a common misconception: black holes do not immediately swallow everything around them. Objects orbit the black hole, gradually losing momentum and spiraling inward. Near the event horizon, the immense gravitational forces stretch objects, shredding them into atomic particles. Some of this matter collects in a rapidly rotating accretion disk just outside the event horizon. Within the accretion disk, friction from collisions between particles generates immense heat, reaching millions of degrees Kelvin. This process produces vast amounts of electromagnetic energy across the spectrum, from visible light to gamma rays. Some quasars also produce powerful jets of material, expelled at nearly the speed of light, which emit radio waves detectable from Earth. How quasars were discovered. The term quasar is short for quasi-stellar radio source. When first identified, quasars appeared star-like but emitted unusually strong radio waves. In the 1950s, astronomers began detecting these mysterious radio sources. In 1962, the first confirmed quasar, 3C273, was located using radio telescopes and lunar occultation techniques. Although it appeared as a faint star in visible light, it emitted vast quantities of radio waves and ultraviolet radiation. The mystery deepened when astronomers analyzed its spectrum. Its absorption lines did not match any known atomic pattern until Martin Schmidt in 1963 recognized them as hydrogen lines shifted significantly towards the red end of the spectrum, a phenomenon known as redshift. This indicated that 3C273 was not within our galaxy but billions of light-years away, making it one of the most luminous objects ever observed. Energy of quasars. Quasars are the most energetic phenomena in the universe, outshining even entire galaxies. The dimmest quasars are at least 10 times more luminous than the Milky Way, while the brightest can be over 100,000 times as luminous. For context, the Milky Way's luminosity is about 25 billion times that of the Sun. A quasar's energy comes from its black hole accreting mass, which is an incredibly efficient process, up to 50 times more efficient than nuclear fusion in stars. To sustain their luminosity, quasars consume vast amounts of matter, around 2 Earth masses per second or 200 Sun-like stars per year. The energy they release can disrupt their surroundings, driving out gas essential for star formation. This phenomenon, known as a quasar tsunami, involves hyperenergetic winds that strip planets of atmospheres and reshape galaxies. The peak quasar epoch. Quasars were most prevalent during the peak quasar epoch, roughly 10 billion years ago, about 4 billion years after the Big Bang. At that time, galaxies were smaller, more gas-rich, and closer together, making galaxy collisions common. These collisions likely fed supermassive black holes with large quantities of gas, igniting quasars. Today, most galaxies, including the Milky Way, have used up much of their gas and experience fewer collisions, making quasars much rarer. Observing quasars today. Quasars are invaluable for studying the early universe. Because light from distant quasars takes billions of years to reach us, observing them is like looking back in time. The closest known quasar, Markarian 231, is about 580 million light-years away, while most are much farther, at distances corresponding to the early universe. The discovery of quasars revolutionized our understanding of black holes and galaxy evolution. Today, more than 750,000 quasars have been catalogued, and advances in technology like the Hubble telescope have provided detailed images of quasars and their host galaxies. Large quasar groups. Quasars are sometimes found in pairs or groups, often due to gravitational lensing, where a massive object distorts the light of a single quasar, making it appear multiple times. However, genuine quasar pairs, triplets, and even quadruplets have been discovered, likely resulting from early universe galaxy collisions. Large-scale quasar groups, some spanning billions of light-years, are among the most massive structures ever detected. Quasars remain a cornerstone in our quest to understand the cosmos. Their study offers insights into the extreme physics of black holes, the evolution of galaxies, and the history of the universe itself. Here's a rewritten and properly punctuated version of the text. Large quasar groups and cosmic structures. We've long known that quasars tend to form clusters in the sky, but we didn't realize just how significant these clusterings could be. First discovered in 1982, a large quasar group, LQG, is a collection of galaxies with active galactic nuclei, arranged in what appear to be sheets, walls, and branches. These structures represent some of the largest and most exotic cosmic formations we've ever observed. Since quasars are products of active, evolving, and interacting galaxies, large quasar groups suggest the early stages of formation for underlying galactic structures, such as galaxy superclusters or other regions of enhanced mass. The quasars illuminate these regions, much like LED lights decorating the branches of a Christmas tree. However, it's crucial to remember that we observe quasars as they were in the early universe when it was much smaller and denser. While galaxy clusters and superclusters today span similar multi-billion light-year dimensions, quasar groups represent structures from the early universe. Discovering structures of this magnitude so early in the universe's life forces us to reconsider assumptions about the distribution of matter and the homogeneity of the cosmos. Cosmic structures and the cosmological principle. One of the fundamental assumptions in cosmology, dating back to Einstein's era, is the cosmological principle. This principle posits that the universe is largely homogeneous, that its contents are evenly distributed on a large enough scale, with only minor fluctuations that average out over vast distances. If this assumption holds true, it should place an upper limit on the size of gravitationally bound cosmic structures. In 2010, astronomer Jason Yadav and his team predicted that the scale of the universe's homogeneity, determined by ripples from the universe's earliest moments, should limit the size of gravitationally bound structures to about 1.2 billion light-years. Finding cosmic structures larger than this limit would challenge some of the most fundamental ideas in cosmology. Yet, many of the largest cosmic structures we've identified far exceed this size benchmark. The question is, are these structures genuinely connected by gravity, or are they artifacts of chance alignments and data processing methods? The largest quasar groups. Of the largest cosmic structures identified, 3 are large quasar groups. The Klaus-Campusano LQG. U1.11. The huge LQG. All 3 are located in a region of the sky near the constellation Leo, identified using data from the Sloan Digital Sky Survey. These structures were studied extensively by astronomer Roger G. Clouse of the University of Central Lancashire. The Klaus-Campusano LQG. Discovered in 1991 by Roger Clouse and Luis Campusano, this structure spans more than 2 billion light-years and contains 34 quasars. At the time, it was the largest known cosmic structure and one of the oldest, with light over 9.5 billion years old. A structure of this size forming so early in the universe presents a significant anomaly in our understanding of the homogeneity scale. U1.11. In 2011, Clouse and his team identified an even larger quasar group in Sloan survey data. This group, dubbed U1.11, contains 38 quasars and extends over 2.5 billion light-years through the constellations Leo and Virgo. It is located around 8.8 billion light-years away and broke its predecessor's 20-year record as the largest known cosmic structure. If verified, it represents an even greater challenge to homogeneity. The huge LQG. Discovered in 2013, the huge Large Quasar Group is the largest of them all, containing 73 quasars and spanning 4 billion light-years. Like the Klaus-Campusano LQG, it lies within the constellation Leo, at a distance of around 9 billion light-years. Some speculate that this group, along with its neighbors, could be part of an even larger cosmic filament, though evidence for such a superstructure has not been found. Seeing patterns in noise. Why are these large quasar groups so incomparably large, even by today's galactic structure standards? Do they force us to reconsider the cosmological principle? Or are they merely artifacts of our data analysis methods? Astronomer Seshadri Nadathur investigated the likelihood of such large quasar groups forming within a random distribution of quasars. Using simulations, Nadathur recreated over 10,000 scenarios with quasars distributed randomly across the sky. He found that apparent superstructures, similar to the huge LQG, occurred in more than 1,000 simulations. This suggests that what we see may not be real gravitationally bound structures but rather patterns arising from statistical noise. As Nadathur succinctly put it, we are merely seeing patterns in noise. Final thoughts. Quasars are rare, highly luminous objects at the centers of massive galaxies. While their groupings may seem significant, further research suggests that their alignment could simply be a chance occurrence. Though these quasar groupings align with dense regions of the universe, they likely don't break any fundamental cosmological concepts. Sadly, due to the universe's expansion, the regions these quasars occupy will soon be beyond our observational reach. Quasars, once common in the early universe, are now exceedingly rare and unlikely to reappear in significant numbers within the Milky Way. While intriguing, the mysteries of quasar groups are reminders of the challenges we face in unraveling the universe's vast complexities.